I am Satvik Urpa from Spire Lab, Indian Institute of Science. I'll be talking about our work on estimating articulatory movements in speech reduction with transformer networks. This is the brief overview of the talk. I'll be first introducing the problem statement, followed by the data set that we'll be using. Then I'll be talking about the proposed approach as well as the experimental setups. Finally, I'll talk about the results and discuss some of the findings and conclude. What is articulatory movement estimation? Articulatory movements represent the movement of vocal tract articulators involved in speech production. These articulators regulate the constriction in the vocal tract and modulate the spectrum of acoustic signal. Paralinguistic information is often encoded in the dynamics involved in vocal tract morphology of the speaker. So we consider estimating these articulatory movements from two different modalities, speech and phonemes. Estimating articulatory movements from acoustic data is known as acoustic-to-articulatory inversion. Here we use MFCC features to represent the speech. MFCC and articulatory movements are computed at an identical rate, resulting in sequences of identical length between these two modalities. So with this formulation, AAI can be modeled as a sequence-to-sequence task. PTA is the task of estimating articulatory movements from phonemes. We use 39 alphabet symbols to represent the phonemes. Here, only the phoneme sequence acts as the input. Timing information is not present. Due to this, there can be a large difference between input sequence length as well as the articulatory movement length. Hence, there is a need for duration modeling to represent phonetic features at a rate identical to that of the articulatory movements. So PTA can be treated as a sequence-to-sequence problem with a duration model. Let me talk about the motivation for this work. Knowledge about the articulatory position along with acoustics is useful in many applications such as automatic speech recognition and speech synthesis. PTA has potential applications like in language tutoring systems for learning correct pronunciation or for analyzing pronunciation defects. Now let us take a look at some of the previous work done in this area. There has been a lot of work done on AAI in the past, including a LSTM model which has achieved state-of-the-art performance. In PTA, hidden Markov models were used in the past, and recently improvement was observed with the Tachytron speech synthesis architecture used for this task. We consider the LSTM and the Tachytron results as baseline for AAI and PTA tasks respectively. Now let me list out the objectives of our work. We'll be utilizing transformer architecture for AAI tasks. We'll be investigating the effect of different positional encodings for AAI transformers. We'll be performing PTA with explicit duration modeling by utilizing a transformer-based speech synthesis architecture known as FastSpeech. We'll also be analyzing the pre-created articulatory movements along with the phoneme level durations predicted by the FastSpeech model. Now, talking about the data set, the stimuli in the data set consists of 460 phonetically balanced English sentences from Mocha timid corpus. Articulatory movement data is collected using electromagnetic articulograph AG501 with a sampling rate of 250 Hz. Audio signals are recorded using a microphone at 48 kHz synchronously with the articulatory data. We use data from 10 subjects comprising of 6 males and 4 females in age group of 20 to 28. After removing the silences, the duration of the recording turns out to be 3.9 hours, where the average duration per subject is 23.4 minutes. We also obtain a phoneme transcription through force alignment. We use 6 sensors for our articulatory movement ground truth, and these are collected with the XY coordinates so that we'll have a 12-dimensional representation for the articulatory movements at each time step. Now, since we'll be utilizing transformers in our work, I'll first talk about transformers. So transformer was first introduced on neural machine translation task in 2017, and in recent years, these architectures have resulted in state-of-the-art performance on various tasks such as speech recognition, speech synthesis. So to briefly talk about the transformer architecture, it has a self-attention mechanism followed by a feed-forward network. Self-attention acts as a feature extraction process. An attention operation is performed along the entire sequence, and dependencies between different positions in the sequence are modeled. Now, this mechanism can be performed multiple times parallelly, resulting in multi-rate attention. And it is followed by a feed-forward network, which combines the information learned by different self-attention blocks. Now, these operations constitute a single transformer layer. We can stack many such layers sequentially, which will form a feed-forward transformer. Now, this feed-forward transformer will be the representation block in our encoder and decoder. The main difference between an LSTM with the transformer is that LSTM processes a sequence autorecursively, whereas transformer can act on it in a single operation, that is the self-attention. The self-attention can be considered as an undirected graph between all the positions in the sequence, and due to this, it can be permutation invariant. And this can result in a loss of sequential information. So in order to avoid this, different types of positional information is explicitly inserted. We considered sinusoidal positional encodings and relative positional embeddings. Now coming to sinusoidal positional encoding, sine and cosine functions of different frequencies are used. The frequencies are determined by values leading up to the required feature dimension of the model. Now these functions are concatenated together and used as positional information along a sequence. Now, what exactly are relative positional embeddings? Well, positional information here is encoded over a small defined receptive field for each position in the sequence. Now, for every position I, position from I minus k to I plus k are regarded as important. And these positions are indexed in a trainable embedding with which features are obtained. Now, these features are added to the self-attention computation so that the relative position information is learned over the course of training. Now, this is the transformer architecture for AI. We'll be using 13-dimensional MFCCs as the input, and we'll first have two linear layers to have a higher feature representation for the MFCCs, and this will be followed by an encoder-decoder structure with the transforms. And we can have different types of positional encodings. We'll first have sinusoidal positional encoding, which can be added or concatenated with the features before passing it to the transformers. Then we can also have relative positional embeddings, and here we'll be using a receptive field of 10 on either side of position in this sequence, and these relative positional embeddings are added inside a transformer operation. Now we also have an experiment with no positional encoding with the assumption that it is present implicitly in MFCCs. Now looking at the architecture for PTA, this is a speech synthesis architecture known as FastSpeech. This is again an encoder-decoder architecture made with transformers, and in the bottleneck it has a duration predictor. And this duration predictor is responsible for the duration model. Now it is made up of few linear layers, and what it does is that for each position in the input sequence, it is going to compute the duration required for that position. Now once the durations are obtained and the encoder output are replicated at each position by the number of times required by these durations. So after this operation, we'll have a sequence length that ideally would represent the actual ground truth articulatory moment length. Now looking at the experimental setups. So we mainly have three different experimental setups, starting with subject dependent setup, where we train a new model on each of the 10 subjects so that we'll have 10 different models. Next, we have pooled training. Here we combine the data from all these subjects and train a single model. Now coming to fine-tune training, we use the pooled model as a pre-trained model and retrain it on each subject to obtain a fine-tuned version. Now looking at how we evaluate this model, we first perform DTW alignment between the predicted and the ground truth articulatory movements. Now we find it necessary to perform DTW mainly because even though ideally we would expect the predicted durations to match the ground truth, in practice it will differ by a bit. And in order to have a fair evaluation, we first need to reduce it to the same length. That is why DTW is used. Now, after the DTW is performed, we compute correlation coefficient and root mean square error metrics on these predictions. Now, looking at the results. So, first of all, let's look at the results for AI with different types of positional encodings. We have 4 different columns here corresponding to the different positional encodings we use, and 3 different rows corresponding to the experimental setups. Now we find that for setup E1, concatenative sinusoidal positional encoding works best, and for setup E2 and E3, we find that relative positional embeddings works best. Now looking at the baseline comparisons, let us first look at the PTA baseline comparison between Tachytron and FastSpeech. Here we find that for setup E1, FastSpeech has a lot of improvement over Tachytron, and this can mainly be attributed to the explicit duration predictor in FastSpeech, whereas in Tachytron it uses an alignment to learn the duration model, and this needs a lot of data to train from. Now looking at setup E2 and E3, we find that there is still improvements in the FastSpeech results in this case as well. Now if we do the baseline comparison for AAI, that is the LSTM versus transformers, we find that transformers are outperforming the LSTM in all the 3 setups. Now finally, we can compare the results between PTA and AAI. Here it will be the comparison between the FastSpeech and the transform model, since they are performing best in their respective tasks. We find that AI results are still much better than PTA, especially in the E2 setup. Now let us compare the predicted durations of the different models. So here we are considering the fine-tuned versions of the model for two different subjects, and we are looking at durations from FastSpeech, tachytron, as well as the ground truth duration. We find that after looking at the differences between these durations, that only in a very few cases are the FastSpeech predicted durations are statistically significant. Now here we will be looking at the predicted trajectories of the FastSpeech model as well as the tachytron model. So in first row, we have the ground truth articulatory movements for LLY and TTY, that is lower lip and tongue tip. And we also have the ground truth duration marked. In the second row, we have the alignment distribution for the tachytron. And in the third row, we have the trajectories predicted by the tachytron. And finally, we have the results from the FastSpeech as well as the predicted durations. Now we can see that the durations are quite similar in the FastSpeech case, whereas in tachytron, it's a distribution and it can vary a bit and there's overlap between different phonemes. And also we can see that with FastSpeech, the trajectories are quite similar. Now, if you look at the complexity analysis for these models, so first of all, looking at PTA, and we see that just by looking at the training time, FastSpeech is performing a lot better than compared to tachytron, where especially in setup E2, FastSpeech takes only 21 minutes to convert, whereas tachytron is 13 hours. And if you look at inference as well, FastSpeech has benefits. Now we can also look at the number of parameters involved in both these models. We find that PTA needs a lot more parameters to learn this mapping, that is 27 million parameters, whereas AI needs only like 1 or 3 million parameters to learn the mapping. Now finally, to conclude our findings, transformers have outperformed the baseline for both PTA and AI tasks. For architectures required for this task, transformer could be a good choice for learning representation for articulatory movement estimation. They have also demonstrated significantly faster training for PTA tasks. Usage of explicit duration modeling for PTA has produced significant improvement. This is very much relevant for training with lesser data. Variations in AI transformer results are observed with different choices of positional encodings. We recommend the use of relative positional embeddings when there is a large amount of data to train from. In order to train with lesser data, using concatenative positional encodings will be the ideal option. Now looking at future work, there is still a significant gap in the results between AAI and PTA. And this exists even though PTA requires a lot more parameters to learn. So we will work on improving the PTA performance in the future. That is it for the talk. Thank you. Feel free to reach out to us if you have any questions or suggestions.